Morph World is a 3D voxel-based simulator used to investigate robot behavior. The goal of the simulation is for the Animat, the small blue box, to move from one end of the world to the other while navigating around obstacles as quickly and efficiently as possible. The simulator uses a genetic algorithm to run the simulation repeatedly over hundreds of generations, optimizing the controller over time to complete the task as quickly and efficiently as possible. Although Morphworld is more abstract than high-fidelity rigid-body physics simulators, it's also more lightweight and efficient, allowing for quicker simulations. By stripping down simulation complexity, research questions can be addressed that involve monitoring many facets of the Animat and its behavior. Each simulation uses a number of randomly generated tunnel worlds, which are generated with a set number of obstacles for the Animat to maneuver around. The placement and orientation of the gaps is random, so the Animat must use what it can sense about the environment to navigate through it. The Animat can sense its environment by using distance sensors, shown by the lines projecting out from the Animat. Each sensor projects out a ray and detects objects only along the ray. Each sensor tells the Animat how far the ray got before encountering an object and are spread out across the Animat in order to allow the Animat to sense an area. In this work, we extend on the idea of a distance sensor to a depth camera. The depth camera produces a depth map of the visible region projected from a single point. By enhancing the sensory capability of the Animat, we allow the controller to interpret an object in totality, thus developing a clearer picture of the world. We want to see if this additional information will allow the Animat to better understand and navigate its environment. The camera sensor functions by casting a number of rays out a certain distance ahead of the Animat. It has a max distance, which is defined prior to the simulation. For example, if we want the sensor to see a 5x5 square, and the user has set the max viewing distance to 10, we can imagine a 5x5 square that's 10 voxels away from the Animat. The sensor will then cast one ray in the direction of each of those voxels on that 5x5 square, forming a pyramid of vision projecting out from the Animat. Each ray will report back how far it made it along the ray before encountering an obstacle, and we normalize that number between 0 and 1 based on the max distance that the sensor can see. In a sense, it's like combining a bunch of distance sensors together at a single point on the Animat and having each of them face in a slightly different direction in order to simulate sight. We conducted several tests with this configuration, but we felt it wasn't really covering enough of an area, so we enlarged the viewing angle of the pyramid. While there could potentially be gaps in the sensor's vision given this larger viewing angle, this effectively allows us to see either a 9x9 or 13x13 area while maintaining the same number of outputs. The trade-off should be acceptable, as objects getting closer will get picked up by the converging rays. Now, in the original configuration, we had 5 distance sensors on the Animat, one in the center and one on each corner, for a total of 5 inputs into our neural network. Now that we have a camera sensor, each sensor provides 25 inputs since it detects a 5x5 area. So we decided to reduce the number of sensors to only one camera sensor on the very center of the Animat. While the depth camera provides an increased vision of the environment, it also leads to longer compute times compared to the single ray distance sensors. Both the single ray distance sensors and the depth camera cast a ray that must be walked from start to finish. They must check if an obstacle occupies the current voxel along the ray, and if so, return the distance traveled before encountering that obstacle. One additional complication of the depth camera is that the depth camera must cast the majority of its rays at an angle, while the single ray sensors always cast a ray straight forward. Sometimes as you walk along the angled ray, 2 or more of the x, y, z coordinates will change, which could either mean one of 2 things. The first possibility is that you went through more than one voxel on accident. In this case, all you need to do is go back to that voxel and check it first before continuing. The second possibility, however, is that you hit an edge or a corner between multiple voxels. In this case, you need to check each of the voxels that share that edge or corner to see if they are occupied by an obstacle. In either case, you will need to walk back and forth along the ray in order to see which condition is true, which also adds to the total compute time for the angled ray. While doing these calculations for a single ray isn't really an issue for a computer, this process can occur one to many times for each ray that the sensor sends out. If you have a 5x5 output for your depth camera, you must compute a total of 25 rays, 24 of which will be angled. While the single ray distance sensors share a generally similar process, they will never be angled and always look directly forward. Thus, they will never encounter an edge or a corner and avoid any additional raycasting costs. Thus, due to the increased number of rays, as well as the generally increased computation cost per ray, the depth camera tends to perform more slowly than the single ray cameras. We ran our sensor with just under 20 different view sizes and neural network configurations, some with around 500 generations, and some eventually going up to 2,500 generations. And overall, the neural network was definitely learning. Although it was gradual, we could see a general upward trend in fitness as the generation count continued to climb, as indicated by the rolling average shown in orange, as well as the higher and higher maximums shown in green. With that said, as compared to the distance sensors, it doesn't appear to evolve effective behavior as quickly. The apparent complexity of the sensor may be preventing rapid adaptation in the population. One of the key issues we observe is that the animat almost always evolves to move right up against an obstacle, rather than staying back so it can see a larger area. For example, if your face is touching a wall, you can't see much of your surrounding environment, and the same is true here. In general, animats tend to shapeshift to be wide or tall and skinny, and sometimes this allows them to move up, down, left, right randomly and find a gap. But in general, they tend to just get stuck. There are a few reasons we think this might be happening. The first is that when you feed a neural network the exact same inputs, such as you are against a wall, it will take a specific action. If you give it the same input, it will take that action again. Thus, since it's right against a wall, it might not be able to make an informed decision about what to do. This, of course, begs the question, why is it up against the wall like that at all? While we haven't conducted a full set of experiments to test this, we suspect it has something to do with the reward function for the animat. As the animat moves forward, we reward it. In a way, we're giving it points for moving forward, and the evolutionary pressure is to get as many points as possible. Thus, the animat itself wants to move forward as much as possible, but this is contradictory to staying further away from an obstacle in order to see more of the environment. It wants to move forward, but if it moves forward, it can't see as well. Going forward, we would likely have to re-engineer the fitness function to favor both forward movement as well as maintaining a larger vision cone. That's all I have for this presentation, but I just want to thank Dr. Moore for his continuous guidance and support over these last 2 years of doing research together, as well as Matthew Shan, my fellow research buddy, for his help with some of the specific coding solutions for this project. He's presenting here at Student Scholars Day as well, so make sure you go check him out too. Thank you.